Calculus, lesson 2. Now trust me when I say we've actually got the worst part of calculus out the way, and that's the monotonous, arduous process that is first principles and understanding all of that. We do have to pay recognition to it and really understand the roots and be able to use that effectively because it is a part of the syllabus. But as you'll see by the end of this lesson, it is so far away from being the best method in terms of differentiating and finding the derivative. And that's what we're going to focus on today. Blowing your mind with an exceptional method that was discovered in order to find the derivative. So lesson 2 is basic differentiation. Now, basic differentiation involves anything with an indice. So in general form, I'm going to say y equals x to the n, which could be x to the 2, x to the 5, x to the half, x to the minus 5, anything x to the power of n, any sort of indice. Now the derivative of that in one step only is done the following way. So what you do with that x to the n is you bring down the power. So whatever the power is, you bring it down. So it becomes nx to the, and you minus 1 from the power. So it's y dash, or the derivative, is equal to n times x to the n minus 1. Bring down the power, minus 1 from the power. That easy. Let's do an example. Y equals x cubed. So let's follow that exact method. You bring down the power, so it becomes 3x, and you minus 1 from the power, squared. Bring down the 3, minus 1 from the 3 becomes 2. So x cubed's derivative is 3x squared. Let's try f of x equals 4x to the 5. So we bring down the power, so we bring down the 5, which times us by that 4. So it'll become 20x to the minus 1 from the power. So minus 1 from the 5 is to the power of 4. Okay. Let's do a couple more. But before that, a couple really important side notes that I want to add to that formula bar that I'm forming along the side there. I've put our first basic differentiation formula, and I want to add these little side notes. First one, when y equals kx, y dash equals k. And what I mean by k is it's any constant. It could be 2x, it could be 17x, it could be minus 8x. So the derivative of those will be 2, 17, minus 8, etc. So in example form, if y equals 3x, the derivative is 3. If y equals minus 14x, the derivative is minus 14. Literally like that. So let's add that to our formula bar on the right there. Now, a second side note. If y equals k, so if y is just a constant, just a number, the derivative is 0. So basically disappears. So if you've got y equals 7, the derivative will become 0. If you've got y equals minus 22, the derivative 0. Y equals 41, the derivative 0. And so on. So let's add that as well. And with that, we're now prepared to take on a few examples. So with the examples, the only thing I want you to remember that's really important is when you've got a few terms, so there we were just working with one term at a time. When you've got a whole statement with a few terms, you can just differentiate them individually, so long as they're separated by a plus or a minus. A times and a divide, we're not even going to worry about at this stage. You can't do it at this stage. So as long as they're separated by a plus or minus, just individually differentiate each term using those rules we've got on the right-hand column there. So, first one, differentiate 5 minus 3x. Well, the derivative will be, the 5 becomes, well, it's a constant, so that becomes 0, that disappears. And the minus 3x becomes minus 3. So the derivative of 5 minus 3x is just minus 3. Second one, y equals x squared plus 2. So the derivative of that, let's differentiate the x squared, bring down the power, minus 1 from the power, so it's 2x, and you minus 1 from the power to the 1, so it's 2x. The 2 differentiated, well, that's a constant, it's just a number, so it becomes 0, so it disappears. So the derivative of x squared plus 2 is just 2x. Okay. Now, I don't know if you recognize those questions there from the first lesson, but those were the exact ones we did by first principles. And I've shown you there all the working that we did for first principles in order to achieve the exact same answer that we just did in one step there. So thanks but no thanks, first principles. You can see how exceptionally short a cut this actually is. Let's move on to a few harder ones. Remember again, when they're separated by a plus or minus, just do them one at a time. Differentiate them individually. So we've got x to the 4 minus 6x. So individually we do the x to the 4, we bring down the power minus 1 from the power, so that becomes 4x cubed. And the minus 6x, that becomes, remember, look at our right hand column, anything with it that's a coefficient of x just becomes that number. So minus 6x becomes minus 6. And that's that done. Next one. 8x cubed minus 9 plus x. Let's differentiate that. We can do it individually because they're separated by a plus or minus. First one, 8x cubed. Bring down the power, minus 1 from the power. So when you bring down the 3, it times us by the 8, so you're left with 24x minus 1 from the power squared. The minus 9 is a number, so that disappears. And the plus x, well, that's just a coefficient of x. So that'll be just plus 1. There's your answer. Number 5. Y equals 6x minus pi x cubed plus root 19x. Now that is one of my infamous intimidators. And I say that because I've especially thrown in pi's and root 19s, all of that stuff just to confuse you. That it's an intimidator. It's there to try to throw you off your game. Don't fall for it. In this case, the important thing to remember is those things that are confusing you, the pi's and the root 19s, they are just numbers. So treat them as just any old number. So let's do this one, differentiating them each individually. 6x becomes 6. Minus pi x cubed, bring down the power minus 1 from the power, so it becomes minus 3 pi x squared. And root 19x is the same as 8x, is the same as 6x, is the same as minus 4x. It just becomes root 19 because it's just the coefficient of the x. And that's the derivative of that. Despite how intimidating it looks, that's your answer. That's the derivative. Done and done.